Okay, welcome back. This last section in Chapter 7 is on fluid pressure and fluid force. Okay, so we're dealing with submerged objects. You may think of something like a window in a submarine, something like that. And you want to know the pressure on that window, okay? The fluid force on that window. So pressure is part of force. Okay? So in order to have a formula for force, we need to have a formula for pressure. Okay, so let's start out with then the fluid pressure. And in particular, it's P equals W times H, where this W is another one of these weight density constants. And all the constants are in the book or online. So in particular, then, P is for pressure on an object at a depth of H. And then W is this weight density. And this time it's per volume. Okay, so in the previous section when we were dealing with the laminar plates, it was per area. Weight density was kind of a matter of area. So, but here it's weight density is going to be in some units like pounds per unit volume. Okay. So in particular then, water, you'll see is, we saw this one before, 62.4 pounds per cubic foot. Or in Newton meters, 9,800 Newton meters cubed. Seawater, just be careful, is a little different. If you put some salt in there, it changes things. It'll be 64.0 pounds per cubic foot. So just be careful. Sometimes you get the wrong answer. It's because you use the wrong weight density. Okay. Alrighty then. So in order to then get the fluid force, you need to multiply the fluid pressure times the area of the object. Okay, so fluid force F is equal to pressure times area. Okay, so P is pressure from above, and A is the area of the object. Okay. We have Pascal's principle in effect here, so orientation will not affect the pressure on the object. Okay, so that's one thing to note. That won't really affect us here in this particular type problem. So part A, we have horizontally oriented surfaces. And that's the simple problem. It's just a matter of multiplying pressure times area. So maybe let's take a look at problem 1. And they're telling us to find the fluid force on a surface, this metal sheet that's submerged in water. Okay, so we have maybe a tank of water. Like this. And then at the bottom of the tank, there's this metal sheet. They tell us the depth of the metal. It's 8 feet below the surface. And then they also tell you the surface area here is 3 feet squared. Okay. They want to know the fluid force. So first, get the pressure, and we're dealing just with, I think it's water this time, so 62.4 will be is our weight density, and then times the depth, which is 8, and then the fluid force will be just the pressure times the surface area that we're dealing with, so times A, which in this case is 3. Okay, so we would end up with 62.4 times 8 times 3. In other words, 1497, and the units will be pounds. Okay. So this is in pounds per cubic foot. This was in feet. The 3 is in feet squared, so the feet cubed all cancel out, and you're just left with the units pounds. Okay, so simple enough. The problem then is the vertical surfaces that we're worried about. And obviously, in real life, you would have surfaces that are maybe tilted not vertically, but at a slant, and then that would be a different sort of scenario. But we keep it easy at first. So vertical surfaces. The way you want to do this is to cut up the sheet into a bunch of little rectangles and then do a summation on the rectangles, figuring out the force increments on each rectangle and adding them up. So number 13, we want to find the fluid force on a submerged plate. We're in newtons meter cubed, so 9,800 newtons per meter cubed will be the weight density of the water. And we have this plate, we'll orient it where the surface of the water is at the x-axis. And then the plate is, the center of the plate is apparently 3 units below the x-axis. The plate is square, it's 1 unit square, okay? 1 meter squared. So it'll look like this. And then we want to find the fluid force on that plate. Okay? So what you'll do is chop it up into a bunch of little rectangles and find the fluid force on each particular rectangle, and then send your running man in this direction, collecting up the fluid force increments this time in his bag of okay, so we need to figure out some values. We need a pressure increment value, and then we need the fluid force increment value, which will be the pressure times the area of the particular rectangle. So first is the pressure increment, and what is that? That's weight density, which we are given as 9,800, times the depth of that particular rectangle. So this particular rectangle is located at position y sub I. It's the width here we'll need later is change in y. So its depth is negative y sub I. So right now this position, if we say it's at -3, the depth would be +3. So we keep that in positive units. So we'll use negative y sub I. Okay. Then the fluid force will just be the pressure increment times the area of this particular rectangle. So the area of that rectangle is this length, which is 2, times the width. Okay, so change in y. So it's a constant 2 times change in y. And then we need the center running man collecting those objects. So that's just the sum of these force increments. And then we take the limit to get our integral, and so that'll equal the integral of 9,800 negative y times 2 times change in y, which is dy. And we're going from apparently -4 to -2. And then you just evaluate that integral. I ended up with 117,600 newtons. So in general, the way this is going to work then, the formula per se is going to be what? The fluid force is equal to, well, what do we need? We need the weight density, right, which we're using a W for. I think there maybe it's a lowercase omega. And then we need its depth. So you'll have some sort of depth function that the book will call H. And then we need an area for the fluid pressure. So that'll be length times width, I guess. So we could use L for length, and then the width is always just going to be dy. Okay, so this is area. Then what else, right? So this part of it, depth times area, is pressure. So you can see all the little elements in the integral. So this would be our pressure. And then finally, whoops, so pressure, geez, what is pressure? Pressure is depth times, sorry, so it's not, that wouldn't be the pressure, right? It's depth times the weight density. This is the pressure right here. And then when you multiply the pressure times the area, then you get the fluid force. Sorry about that. Okay. But my point is, these integrals, they're very flexible, and if you're trying to memorize them at the end of the day, you kind of have the formula embedded in the integral there. Anyways, let's look at another one. This time it's finding pressure on the gasoline tank. Okay, so problem 21. We want to find the fluid force on, I guess, the back of the gasoline tank. So 7.6, let me make sure. No, 7.7 now. So a cylindrical gasoline tank is placed so the axis of the symmetry of the cylinder is horizontal. Find the fluid force on the circular end of the tank when the tank is half full. So you're dealing with one of these gas, like you see kind of on the back of semi trucks. It's one of these things, this tank here, and they're saying it's half full. And in particular, they're worried about the pressure on the back of the tank. So the pressure on this plate right here. Okay, so what we're going to do is orient the plate at the origin. Okay, it's half full, so I need to find the fluid force on this region here. They're telling us the weight density of gasoline is 42 pounds per cubic foot. And what else they tell us? The diameter of this plate is 3 feet. So from here to here, it's 1.5. The radius of this particular plate is 1.5 feet. Okay, so again, you need to figure out your pressure increment and then get your fluid force increment, and then send your running man to collect all of those values, all of these fluid force pressure, or the fluid force values for the particular rectangles from here this time to here. Okay, so for the pressure increment, I need the density times the depth. So the depth for, if I'm worried about this position, this particular rectangle located at position y sub I, the depth is going to be negative y sub I. Okay? So that's easy enough. The fluid force, then I take the pressure increment and multiply it by the area of this rectangle. To get the area of the rectangle, I need basically the formula for this circle to give me the radius. The radius is half the length of this rectangle, so it's going to be, I'm going to need to multiply it by 2, whatever the heck it is, and then times the width of the rectangle. So I need a formula that tells me at any particular given position y sub I, what is the distance from here to here. Right? Okay, so the formula then is just the formula for this circle. In particular, we have x squared plus y squared is equal to 1.5 squared. 1.5 squared is 2.25. Okay. Then what do? We want to solve it for x. So x will be plus or minus square root of 2.25 minus y squared. Okay, so this side, this hemisphere of the circle is given by the positive root, this guy. So our formula to get this distance from here to here for any particular y sub I is this formula. We need to multiply it by 2 to get the entire length. So it's 2 times that formula, 2 times the square root of 2.25 minus y squared. Okay? Because I need the area of this rectangle, not just half the area of the rectangle. Okay, finally then I can dump it into my integral. So I'll have our omega is 42 times our y times all kinds of other good stuff, right? There's a 2 in there. There's this square root thing, 2.25 minus y squared. Then there's the dy. And we're going from negative 1.5 to 0. Okay, integrate that. I got 94.5 pounds. Okay, thanks for watching.